All right, welcome to the Explainer. Today, we're going to jump into some really fascinating code that answers a huge question in our digital lives. How can you prove something's true without, spilling all your secrets? We're going to walk through a solution that is just so elegant and powerful. So picture this. There's a massive guest list for some super exclusive event. You know your name's on it, but you gotta prove it to the bouncer. The catch? For privacy, you can't just hand over the entire list. So what do? That's the exact problem our code is built to solve. It's all about verifying one little piece of data inside a giant data set and doing it securely and privately. Okay, here's how we're going to break this down. First, we'll look at the proof itself. Then, we'll see what evidence our code needs to climb this data tree. We'll check out the final moment of truth, and then wrap up with why this whole thing is such a big deal.
All right, section 1. So what is this clever little solution? Well, it's called a Merkle-proof. And trust me, it's the key to proving something exists without showing your whole hand.
So, a Merkle-proof, what is it?
It's our answer. And the core idea is pretty brilliant. Instead of sharing the entire data set, the whole tree, so to speak, you only share your specific little piece of data, your leaf. And you prove it belongs there by providing this tiny path of cryptographic fingerprints, we call them hashes, that connect your leaf all the way to the top. It's super small, incredibly efficient, and totally secure.
Okay, so to actually verify one of these proofs, our code needs a few key pieces of evidence. Let's dig into the 4 ingredients it needs to start its check.
Right, so our code needs 4 things. First up, the leaf. Think of this as your ticket. It's the unique fingerprint of your data. Second, we have the path elements. These are like your companion's tickets. They're the fingerprints of the data next door at each step up the tree. Third is path indices. This is basically your map, just telling you to go left or right. And finally, you have the root. This is the big one, the known fingerprint of the entire data set. It's our final checkpoint.
Okay, this next part, this is the heart of the whole process. We've got our ticket, our directions, and our companion's info. We are ready to climb. So let's follow the code as it tries to rebuild the path from our one single leaf all the way back up to the root. So where does the journey begin? Right at the bottom. The code grabs our leaf, that's the hash of our specific piece of data, and it treats that as the very first step of the climb. Every single step after this is going to build on this one starting point.
Now, our guide for this climb is that path indices array we talked about, and honestly, it's just a simple map. At each level of the tree, the code looks at the next number. If it's a 0, that means our current spot is on the left. If it's a 1, we're on the right. Simple as that. This is what tells the code how to combine the hashes at every single step.
But wait, how can the code actually trust these directions? I mean, what if someone tries to trick it? Well, it uses this really clever mathematical constraint. You see, the equation x times 1 minus x equals 0 is only true if x is either 0 or 1. There are no other possibilities. By forcing this rule, the code guarantees the path can only be made of left or right turns. Any other funny business, and the proof just fails. Instantly. Okay, so the climb begins. The code just loops through these 4 simple steps over and over for every level of the tree. Step 1, check the direction. Is it a 0 for left or a 1 for right? Step 2, grab our current hash and the sibling hash for that level. Step 3, using that direction, it smashes them together in the right order to calculate the parent hash. And finally, step 4, that new parent hash becomes our new current position for the next level up. Rinse and repeat, and that's basically it. This process of check, combine, and climb just repeats n times, once for every level in the tree. With each loop, we're getting higher and higher until finally we've computed our way to what should be the very top. And here's the crazy part. For a list with, say, 1 million items, this entire climb only takes about 20 steps. It's incredibly efficient. All right, after all that climbing, we've made it. We've reached the summit, the code has spit out a final hash, which should be the root of the whole tree. Now comes the moment of truth. So after n loops, 1 for each level of the tree, the code has produced one final single hash. This is the very last value in our intermediate hashes array. It represents the root of the tree, but it's the version we calculated ourselves, starting from our little leaf and following the path. And this, right here, is the million-dollar question. The entire validity of our proof, everything we've done, it all hangs on the answer to this. Remember that official root hash we were given at the very beginning, our final checkpoint? Does the root we just calculated on our journey match that official one? The code checks this in a really specific way. See, in the world of zero-knowledge circuits, you don't just ask, hey, are these two things equal? No, that's not how it works. You have to prove they're equal. And you do that by subtracting one from the other, and then constraining the result to be 0. It's a much stronger way to prove it, and it's key to the integrity of the whole system.
If that proof is valid, this is the only number you want to see. 0. A big, fat 0. A difference of 0 means our leaf, combined with the path elements following those directions, perfectly, and I mean perfectly, recreates the official root hash. It's the mathematical stamp of approval. It proves our ticket is legit. The proof is valid.
So we just walked through the logic of what is really just a few lines of code. But the implications, they're absolutely massive. So let's talk about why this simple-looking code actually matters so much.
I mean, look at what this code actually achieves. It lets you prove you're part of a set without revealing the whole set. That's why it's so fundamental for massive systems like blockchains. It makes verification super efficient, it guarantees that your data is intact, and that it's private, all at the same time. This is the real power of zero-knowledge proofs, using simple, repeatable logic to solve these incredibly complex problems of trust in our digital world.
And all this leaves us with a pretty cool final thought. If we can prove that one little thing is part of a massive dataset with such a small, private proof, what else can we verify? I mean, think about it. You could prove your age without showing your birthday. You could prove your credit score without handing over your entire financial history. This kind of technology really does open up a whole new frontier for trust and privacy, all built on the kind of elegant logic we just walked through.